push that rock here with some math. So to understand this video, you have to know what a squeeze box is, aka the musical instrument known as an accordion. And I have a picture here that I drew in case you haven't seen one, but it's an instrument that has these flexible folds in the middle, and you can squeeze it and it changes the output of the sound. So, and you can go back and forth with it, so you can widen it and then close it. So anyway, it's called a squeeze box because you squeeze it closed. Okay, so that leads me to the squeeze box theorem. It says that if you have y is a trig function and you have this frequency, what I'm going to call the coefficient on x, or the frequency number, I'm going to call this the frequency coefficient. If you have a frequency coefficient here, then the least period of this function is equal to the least period of trig of x divided by the frequency coefficient. Let's do an example. So here we have this. So I take the least period of this function is going to equal the least period of a tangent function. Well, the tangent function's least period is pi. Okay, for tangent and cotangent, the least period is pi. For sine and cosine and its reciprocals, the least period is 2 pi. But for tangent and cotangent, it's 1 pi. So I take the least period of the trig function and I divide by the frequency coefficient. And that's my least period. And now I'm ready to draw a tangent wave. Now when I say graph a tangent, a trig function, we mean graph at least one cycle. So we'll graph at least one cycle. So here we go. Now we know that the important output for tangent is 1 and -1. So we'll put that on here. And then we need some tick marks on our horizontal axis. And now the least period, normally I think of this, I go from pi halves to pi halves because half a pi plus half a pi is a full pi, and that would be the least period. And then this would be, if this is pi halves, this would be pi fourth, and it would go through 1, and there'd be an asymptote here, and it would go through -1 at negative pi fourths, and there'd be an asymptote here, and it comes up and it does this. And it's going to do the exact same thing, but my period has changed. Okay, so since my period has changed, I need this full length over which I'm going to draw a cycle. Let's go ahead and draw the tangent wave. And there's the tangent wave, okay? Goes through 0, 0, okay. Now, but I need this full length of the domain, this full interval of the domain from here to here that contains one cycle of my tangent wave to be equal to pi thirds. Well, if this full distance is pi thirds, then half of it would be pi 6. So this is pi 6 right here. And then this would be pi 12ths. And then that would make this negative pi 12ths. And then this would be negative pi 6. And there's my tangent wave. If you come over one more unit, you'll see the wave starting over again, you know. So the asymptote continues here. So there's another wave over here, of course, and it's coming up, and it will hit -1 here, and it'll hit 0 here, and it'll continue, and it's going to continue on this other side too. So it's over here as well, but we have one cycle. That's all we needed. Now let's test that. Let's test and see if we put in pi 12ths into our function that we really get out 1. So tangent of 3 times pi 12ths. Well, that's tangent of 3 goes down on 12. We get 4th, and sure enough, tangent of pi 4ths is 1. Check. Math made simple. Simple math.